Hello everyone and welcome back to Learn with Rita. I'm Rita, I'm currently a software engineer at Amazon. I love machine learning, artificial intelligence, and basically everything that has to do with mathematics. And through this channel, I want to share my passion with you all. In today's video, we're gonna go over the proof for the one-sided Chebyshev inequality. So let's get into it. So, the one-sided Chebyshev inequality states that for a zero mean random variable x with variance sigma squared, we have the probability of x being higher or equal the probability of the random variable x, the value of this random variable x being higher or equal than b, is upper bounded by the quotient of sigma squared over sigma squared plus b squared. And this is for any b strictly higher than 0, as you can see here. So the goal of this video is for us to go over the proof of this inequality. So the first thing that we're going to do is we're going to write down the mathematical formula for the variance for x, which is a real random variable. So it takes real values. And we're going to write that down, and we're also going to write it down in a way that will allow us to derive the proof. So now that we have written down the mathematical formula for the variance, which is sigma squared, you can see here that we have defined it in terms of b. And just a quick note here, you can see that there is a minus right here on top of the b, and that just basically means that we are excluding b from the interval, the integration interval that we are using here, because we are already including it in the other integration interval. So now let's just erase these two circles, and we're gonna call this integral number 1 and integral number 2. So at this point, we're also going to give a name to this probability p of x higher or equal to b. We're going to call it beta, because in the end it is a constant. So the first thing that we want to do is we're going to show that the integral number 2 satisfies the following inequality. The way we're going to go about proving that integral number 2 satisfies this inequality is we're just going to start with what we have. What do we have for now? We know that we're going to consider b that is higher than 0, strictly higher than 0, and that we are integrating, so the x that we are integrating over will range from b to plus infinity, which means that x is higher or equal to b. And this is all we're going to start with. The fact that x is higher or equal than b, and that b is strictly higher than 0, means that we can apply the square function to this inequality without it changing the direction of the inequality. Why is this the case? This is because the square function is increasing on the interval from 0 to plus infinity. And given that we are making the assumption that b is strictly higher than 0, then it is increasing on this interval. From then on, we go on to multiply with the probability density function px by evaluating it in x. And the reason that multiplying by px of x also doesn't change the direction of this inequality is because of the inherent definition of a probability density function. Given that px of x is a probability density function, by definition means that px of x is higher or equal than 0. So far, so good. Now, we're gonna use the increasing property of the integral to integrate over this inequality and maintain still the direction of the inequality. We're gonna integrate over our integration interval here. And this is an integration over x on both sides of the inequality. All right. And this is because of the increasing property of the integral. Now we use the linearity property of the integral to take out this p squared from the integral to outside the integral, because b squared is a constant, and so given the linearity of the integral, we can just take it out of the integral. Now, this is where it gets interesting. You can notice here that this entity that we just found is actually the definition of beta. This is the definition, this is how we define mathematically p of x higher or equal than b, which is actually beta. Hence, we have just proven our first inequality. Now, what we want to show is that the following two conditions are met. We have a condition on the integral from minus infinity to b minus of p of x, and then we have a similar condition on x p of x. That is actually inequality. So the first one is actually pretty easy to show. We're just gonna call it A and then B. So for A, this actually stems from the definition of probability. So the integral, we know that the integral from minus infinity to plus infinity p of x, px of x is equal to 1. And we know that we can rewrite this integral to make it depend on b. b minus px of x dx plus b plus infinity x of x dx is equal to 1. And we know that this entity is actually equal to beta. This is p of x higher or equal than b, and this is beta. Hence, we get the equation that we got above. This first one was pretty straightforward to do. Now let's take a look at how we can prove our second equation here. And what we're going to use here is the definition of the expectation value of the random variable x. So we know that x is zero mean, which allows us to say the following. So we're just going to write down what zero mean actually means, and from there on we're gonna derive the inequality that we were asked to show. So the mean, the expectation value, so the mean, is written as follows. So minus infinity plus infinity so it's the integral over the whole over r of x times the probability density function over R, and this is the definition, and this is equal to 0, which means that if we split this up and express it in terms of B, we're gonna see the one part of what we're trying to prove show up. So we have the integral from minus infinity to b minus plus from b to plus infinity x times px of x dx, and this is all equal to 0, which means that ultimately the integral from minus infinity b minus x px times x dx is actually equal to minus this integral right here, and then we're gonna use this integral. This is the integral that we're actually gonna use for our calculation, so this is just an intermediary step that will allow us to reach the final conclusion that this entity here is less than minus b times beta. And so to do that, we're just rewriting this entity in terms of the other entity that will allow us to reach that upper bound, and thus allowing us to prove that inequality right there. So here we have just shown that we can, given the fact that x is a random variable with 0 mean, it actually means that the expectation it actually means that the expectation value e of x can be written this way, which allows us to reach this temporary conclusion right here. All right, and now given that we have found this equivalence between these two formulas, we're gonna find an upper bound for this first formula by leveraging the knowledge that we have about this second formula. What we're gonna do now is we're gonna use a similar approach to what we have seen in the first question of the first thing that we have proven in this video. So in order to reach that inequality, we're gonna leverage the same tools that we have used a bit earlier on in this video, and we're just gonna use a similar approach by using these values here, and then we're just gonna build up from there. So we know that x here takes values from b to plus infinity, and we're just gonna rewrite that. So for any b strictly higher than 0, and for any x higher or equal than b, we have x times px of x higher or equal than b times px of x. Again, because of the positive nature of the probability density function, by definition, this entity that we're multiplying both sides of this inequality with is higher than 0, which maintains the direction of the inequality. This allows us to integrate from b to plus infinity, again using the increasing property of the integral, and then we're going to use this to invert. Well, before inverting, let's just start with computing this second entity right here, also here using the same approach as earlier. So px of x dx, and this is going to be equal to b times beta, which the b we're taking out of the integral because of linearity, and the beta is obtained by integrating p of x over this interval right here, and which we have seen corresponds to the definition of beta, which is p of x higher equal than b. This is just a small reminder. So let's just rewrite this inequality right here. This leads to b plus infinity x px x dx is higher equal than b times beta, and what we're actually looking for is the minus of this entity, and since we're gonna multiply then this inequality by -1, and this time it will cause us to invert the direction of the inequality because we are multiplying by a negative value. And so minus plus infinity x px of x times dx is going to be less than minus b times beta, and what we have just shown here before allows us to say that this is none other than the entity that we were defining earlier. b minus x times px of x dx is lower than minus b times beta, and we have proven what we wanted to prove right here. And now what we're gonna do is we're gonna define a new function which is called py, and this is, we're gonna prove that it's actually also a probability density function, and yeah, this will give you some insight into what it means to be a probability density function and how you can prove it. And yeah, that's exactly what we're gonna do. So let's just write down what this probability density function that we're gonna prove looks like. So let's just write it down. So step number 3, and we're just gonna define it here. Now, what we need to do is use what we have just proven in the previous question, in the previous part, to show that py of y is actually also a probability density function. What does it mean to be a probability density function? What we need to prove is that for any y in the set of real numbers, that any y in the set of real numbers, that py of y is higher or equal than 0. Well, we can obviously see here that for y higher than b, it's equal to 0, so this inequality is satisfied. The other thing that we can see is that for y less than b minus, we have a multiple here between px, the probability density of x evaluated in y, and this entity here, 1 over 1 minus beta. This entity is actually the one that we need to prove that is higher than 0. And so we're just gonna do a quick back of the napkin math to show that this is actually true. And actually, it's quite simple. It has to do with the definition of beta, obviously. So we know that the probability of x higher equal than b plus the probability of x less than b is equal to 1, because here we are covering the whole space of possibilities, which is the set of real numbers. And so, since this is equal to beta, this entity here, 1 minus beta, is actually a probability. And it represents the probability of x less than b. And since it's a probability, it is always higher or equal to 0. Therefore, even if we invert it, even if we do 1 over this entity, it doesn't really matter because the sign won't change. And therefore, 1 over 1 minus beta times px of y is going to be higher or equal than 0. Therefore, proving that for any y times r, 0 higher or equal than 0. This is for the other part of the equation. Anyway, we have proven that py of y is higher or equal than 0. So this is the first part of proving that a function is a probability density function. The second part that we need to prove is that we need to integrate over the space of possibilities. Here again, this is the space of possibilities is the set of real numbers, and so we need to integrate this function over r, so minus infinity plus infinity py of y dy. So we're integrating over y naturally because that's the variable that we're using here. We need to prove that this is equal to 1. Let's prove that the integral of p of y over r, which is the set of real numbers again, is equal to 1. And so in order to do that, we're just going to write down this integral by splitting it into the different parts of the integral. So we're just going to split it, and we're going to go from minus infinity to b minus, and this is going to be the first part of the integral, 1 minus beta, 1 over 1 minus beta times px of y over dy plus the integral from b to plus infinity of 0 times dy, and this is equal to 0. So we don't have to worry about this, and so we're just gonna call this I so that we can continue putting equal signs here at the bottom. And so at this point, what we need to do, yes, at this point we're just gonna use what we have just proven here. We're just gonna use this part here to prove that this integral is equal to 1, and it's pretty straightforward. We're just going to use the linearity of the integral and replace the value of this integral. So 1 over 1 minus beta times px of y dy. Keep in mind that like this y here doesn't really matter what we call it. You can call it a, b, c, d, well, not d because we have a dy because it means differential.
ABC, X, Y, doesn't matter. So this entity here is actually the same as this entity. So we can just replace those two entities, and we can replace that value by y 1 minus beta. So this entity is actually equal to 1 minus beta. Hence, we reach this point where we have 1 minus beta times 1 minus beta, and these 1 minus betas just cancel out.
And therefore, we just have proven that the integral from minus infinity to plus infinity of py of y of dy is equal to 1. Therefore, completely proving that py is a probability density function. Yay! Now that we have proven that py is a probability density function, we can leverage that to use the expectation function and some formulas used in y to entail or just to find out some new information about the equations that we are trying to come up with on top, or the integrals that we have come up with. Also, you might have noticed that I've changed my clothes, and this is another day, so let's just continue with the proof. So, at this point, now that we have proven that py is a probability density function, we can leverage that to infer some things about one of the inequalities that we're going to be using later on. And so right now, what we're going to want to show is that we can rewrite this, this integral right here into something that's expressed in terms of y, and here we want to show that this integral can be written as this formula, or this inequality, that the constraint on this integral can be rewritten as this constraint on the expectation function of y. So now let's prove this inequality, that this inequality is equivalent to the inequality in terms of y. So the way that we're gonna show that the bound on this integral that we have here, that we have just proven in the question above, or not that long ago, is equivalent to this bound right here that's dependent on y, and that we can express in terms of the expectation function of y. The way we're gonna do that is we're just gonna rewrite, write the definition of the expectation function of y, and by writing the definition of this expectation function and just basically using the definition of the probability density function of y, we're just going to use that in order to derive this equation. So the expectation function of y is the integral from minus infinity to plus infinity of y times py of y times dy, and this is none other than the integral from minus infinity to b minus of y times 1 minus 1 minus beta times px of y times dy plus the integral from b to plus infinity of 0, basically, and that's just gonna be, we're just gonna write it down here so that we don't forget that actually this is just a special case, because the probability density function is 0 on the other integral, on the other interval we're integrating over. Okay, And this is none other than one. Well, we'll take out this constant here, and we're just gonna rewrite this in terms of the previous integral that we have the bound on, and this is no other than px of y dy, and we can see here that this is exactly the integral that we have a bound on that we have shown previously, you know. It's just that here we are using y as a variable, and it doesn't really matter because we can call this as we have seen earlier, a, b, c, y, x, etc. It doesn't really matter, but we actually have a bound for this, and we're just gonna have express a bound for the expectation function of y by leveraging the bound that we have on this integral. And so this integral is less than minus b beta from what we have previously shown. And this will just allow us to draw that conclusion that actually e y is less than 1 over 1 minus beta times minus b beta, which is exactly what we're looking to prove, and we're just gonna rewrite it in a way that removes this one here. Okay, let's redo this. And we're just gonna remove this one and then just basically move this part here because it's basically the same thing. And there we have it. We have just proven that this bound that we have can be translated in well, we have just shown that this bound that we had proven in a previous question can be translated into a bound on the expectation function of the random variable y. And so, yeah, we can just use this to move to later on. Yeah, we can just use this later on to reach the final conclusion of the Chebyshev inequality. So, given that we are now in the business of translating bounds that we have on the integrals that we're trying to compute to in terms of the random variable y, we're also going to show that 1, which is the integral from minus infinity to b minus of x squared p x of x dx can be rewritten in terms of y, and we are looking for a specific formula that will allow us to come to our conclusion of the Chebyshev inequality. And so let me just write that down. Now show that 1, meaning which is the integral from minus infinity to b minus of x squared p of x dx. So this is the integral number 1. We're just going to show that 1 can be rewritten as as 1 minus beta times the expectation of y squared. Basically, what we're going to do, we're just going to use a similar approach by writing down the definition of the expectation function of y squared and then come out to the conclusion that that the integral number 1 is equal to this formula depending on the expectation function of y squared. So let's just dive in. So let's just write down the definition of the expectation function of y squared. And here we're just going to use the law of the unconscious statistician, which states that for any function j, if we compute j of x, or in this case j of y, then it's equivalent to the integral over r of j of x times px of x dx, and here we're just gonna use the random variable y instead of x, and the function j will be in our case the square function. So let's just write it down. So the expectation function of y squared is equal to the integral over r, so from minus infinity to plus infinity. So this is the definition. From minus infinity to plus infinity of y squared times py of y dy. And we're just gonna rewrite this, and this is similar to what we've just done above. Minus the integral from minus infinity to b minus of y squared times 1 over 1 minus beta px of y dy, and we have the zero term because for the same reasons, basically, because the probability density function over that interval is equal to 0, and so we just can ignore the integral over that interval again. And here, similarly to what we've just done, we're gonna take out the constant 1 over 1 minus beta from the integral using the linearity property again of the integral, and this will allow us to come to the conclusion that we've just made, and here px of y dy, and here we can also identify the integral number 1 that we've defined, hence we can just multiply the other side by this 1 over by this 1 minus beta, and thus coming to the conclusion that the integral number 1 can be rewritten as 1 minus beta times the expectation function of x squared. So let's just write the conclusion down, and yeah, just so that we can close those loops and just have it complete in our minds that we have actually proven this of minus infinity minus 1 x squared. It doesn't matter if we put here again use the integration variable as x or y. It doesn't really matter as long as the functions that we're integrating over are not dependent on another variable. It doesn't really matter. So dx. Therefore, we have come to the conclusion of what we wanted to prove. We have just proven what we wanted to prove. And now we can move on to the next question. Moving on, let's rewrite this. Okay. So here what we're gonna do is we're gonna use the fact that for any random variable z, for any random variable z, we have that the expectation of z squared is less or equal than the expectation of the random variable z squared, okay? And this can be easily proven by just using some formulas and reaching this conclusion. We're not gonna get into that proof today, so we're just gonna take this for granted. And yeah, if you want me to make a video proving this inequality, please let me know in the comments so that I can actually make that proof. Otherwise, this video would be 10 hours long and we would not be done with proving our Chebyshev inequality. So let's just stay focused on this, proving the Chebyshev inequality so that we can leverage that in future instances. Anyway, we're just gonna leverage this this inequality that we have on any random variable. So this is true for any random variable. Okay, and we're just gonna use this to show that there is some sort of upper bound for the integral number 1, and yeah, let's just use that as well as the bounds that we have just or like the expressions that we have just found of the expectations function of some integrals that are interesting to us in terms of y. And so yeah, the only reason that we have defined this probability density function y is to make it easier for us to come out to get to some specific conclusions. And yeah, like that's the only reason we have to define this. We don't have any inherent interest on all of these properties that we have or basically conclusions that we have come to for the probability density function of y, but we are only interested in leveraging the information that we get from y to get to our final goal, which is to prove the one-sided Chebyshev inequality. So, okay, so now what we're gonna do, let me just write it down. What we want to use is we want to use this property and the bounds that we have just found for y and y squared, well, expectation of y and expectation of y squared, to show that the integral 1 is lower bounded by some specific bound. And then we're gonna also build on this and come up to another conclusion. And ultimately, we are almost there. We have almost proven the one-sided Chebyshev inequality. So yeah, let's just do this. Okay, let's just write down what we have for now. Okay. So what do we have now? What have we just proven? We have just proven that the expectation function of y is less than minus b times beta over 1 minus beta, and that 1 minus beta times expectation of y squared is equal to this integral number 1 that we're looking for. So minus infinity b minus x squared px of x dx. Okay, this is what we have. Okay, so at this point, what we want to do is we want to leverage this inequality in terms of the random variable y's. So the expectation of y, all of it squared, is less than the expectation of the random variable y squared. And we're just gonna use the bound that we have on ey that we have just used. So we're just gonna rewrite this bound and translate it into a bound on ey squared. So beta 1 minus beta. So we have this inequality, and so given that this whole entity right here is less than 0, what we can do is, if we square this on both sides, the square function is decreasing on 0 on the interval from -infinity to 0, and we're just going to leverage that, which means that this inequality will actually be reversed once we apply the square function to it. So this square function thing is going to be more than b squared beta squared 1 minus beta squared. Okay? So this is what we know. We also know that this whole entity, e of y squared, is less than e of y, as per basically what we have just talked about. And so this thing is a lower bound on this. So b squared beta squared 1 minus beta squared. And this part right here, so we can just say that b squared beta squared 1 minus beta squared is less than expectation of y squared. Hence, if we multiply both sides by 1 minus beta, we get the inequality that we were looking for in terms of 1 minus beta times expectation of y squared, and this is exactly the integral number 1, which is the integral from -infinity to beta minus of x squared times bx of x dx. And this is what we wanted to show, and so let's just write the final conclusion on this, that the integral from -infinity to b minus has a lower bound, that is, to b minus has a lower bound, that is what we have just shown. X has a lower bound, which is b squared beta squared 1 minus beta. And let's just highlight this in this way. Okay, done. Now we're just gonna combine this lower bound that we have found for integral number 1 with the bound that we have found for integral number 2 way before, which was the first thing that we have proven, in order to come up for a lower bound also for the variance. So we have shown, we have the following two equations. So from b, 2 plus infinity is equal to x squared p of x dx is higher than, has as a lower bound b squared beta, and what we have just proven here is the other inequality. So let's just rewrite it one more time. B minus e squared x of x dx b squared beta squared 1 over beta. So we're just gonna add these two inequalities together. Keep in mind that both of these inequalities are higher or equal than 0, and we can actually just add them up. Hence, sigma squared, which is the sum of these two, so just gonna put an addition here, and this is gonna be equal to sigma squared higher or equal than b squared beta plus b squared beta squared 1 minus beta. Okay? And we're just gonna reduce this to come up with a final bound on sigma squared. And so it's gonna be 1 minus beta times b squared beta plus beta squared b squared beta squared over 1 minus beta. And here we can see that this term is actually repeated by the multiplication of this term with this term. And in the end, we're just going to keep this term, the multiplication of these two terms, and this term slash this term will zero out with this one. And then we can just write down this, that sigma squared is higher equal than b squared beta over 1 minus beta. And this is the final conclusion for this part of the equation. So at this point, what we're gonna do, we're just gonna leverage this inequality that we have just found and basically rewrite it in a more convenient way to derive the Chebyshev inequality. All we have to do, we have proven everything that we need to do in order to prove the Chebyshev inequality at this point. And so let's just rewrite this into a more convenient way for us. So we're just gonna multiply each side. We're gonna try to isolate the beta from the other variables, and that is what will allow us to write the Chebyshev inequality. So let's just rewrite this inequality here in a way that will allow us to isolate the beta. So we're just gonna rewrite this in terms of 1 minus beta. We're just gonna pass this on to this side. So 1 minus beta times sigma squared higher equal than b squared beta. Therefore, we're just gonna try and isolate the beta. So this is equivalent to sigma squared minus beta sigma squared less than beta squared b squared beta. And then we're just gonna put the betas in the same on the same side of the inequality, and so this is equivalent to having b squared plus beta plus b squared times beta plus sigma squared times beta. We can isolate out the beta and then pass down this into b squared. So this is sigma squared plus b squared times beta, and the final conclusion is that beta is less than sigma squared over sigma squared plus beta b squared. And this is no other than the one-sided Chebyshev inequality, because this is equal to p of x higher or equal than b. So we have just proven that for any random variable x, for any b strictly higher than 0, we have just proven that the one-sided Chebyshev inequality is met. P of x less higher or equal than b is always less than the sigma squared and this is the one-sided Chebyshev inequality. So I just want to give a shout out to my professor, Professor Mathieu Bloch from Georgia Tech. This proof and this material that I've just shared is actually comes from that class that I have taken a few years back. And yeah, I just keep coming back to this class. It's because the content was so good. So thank you so much, Professor Bloch, for the amazing content. And I'm just trying to share the knowledge that I have learned in your class to a wider audience. So I did not make up this whole problem. And yeah, just wanted to put that out there because I don't want to take credit for something that I did not put together. And so right now I'm just sharing my resolution of that problem that Professor Bloch had given us in one of our assignments, and I was just enjoying solving such problems again. So thank you, Professor Bloch. If you enjoyed my proof of the one-sided Chebyshev inequality and would like to see other proofs like this or explorations of mathematics and machine learning and any mathematics related topic, please click below on the subscribe button and the notification bell so that you can be notified whenever I put out new videos. And please leave in the comments any theorems that you would like me to do a proof of. And yeah, click here to watch my latest video.